In the depths of the Atacama Desert, where the air is so thin and dry that it feels like standing on another planet, Dr. Sarah Chen stares at her computer screen in disbelief. The numbers don't make sense. According to her calculations, based on 20 years of observations from the most powerful telescopes on Earth and in space, the universe should contain nearly 10 times more small galaxies than we can actually observe. Somewhere in the cosmic accounting, trillions upon trillions of galaxies have simply vanished from our census of the cosmos. It's 3 in the morning, and the only sounds in the control room are the gentle hum of cooling fans and the distant wind across the Atacama's ancient, lifeless plains. Dr. Chen has been working on this problem for months, cross-referencing data from the Hubble Space Telescope, the James Webb Space Telescope, and ground-based surveys that have mapped millions of galaxies across billions of light years. Every analysis leads to the same impossible conclusion. The universe is missing most of its galaxies. This isn't a simple matter of observational limitations or telescope sensitivity. The missing galaxies should be bright enough to detect, numerous enough to dominate the cosmic landscape, and fundamental enough to our understanding of how the universe works that their absence calls into question everything we thought we knew about cosmic evolution. Dr. Chen realizes she's not just looking at a data discrepancy. She's staring into one of the deepest mysteries in modern cosmology. The story of the missing galaxies begins with a prediction that seemed so solid, so mathematically inevitable, that astronomers spent decades simply assuming it must be true. Computer simulations of cosmic evolution, based on our best understanding of dark matter and the fundamental forces that shape the universe, consistently predict that space should be filled with countless small galaxies, each containing millions or tens of millions of stars. These simulations start with the cosmic microwave background, that faint afterglow of the Big Bang that we can still detect today, and follow the gravitational collapse of matter over billions of years. Dark matter, that mysterious substance that makes up roughly 27% of the universe, forms an invisible scaffolding throughout space. Normal matter, the protons, neutrons, and electrons that make up stars, planets, and ourselves, follows this dark matter framework, collecting in gravitational wells and eventually igniting as the first generation of stars. According to these models, the universe should be absolutely teeming with dwarf galaxies. For every large galaxy like our Milky Way, there should be hundreds or even thousands of smaller companions, each a self-contained stellar city with its own history of star formation, stellar death, and chemical evolution. The mathematics is elegant, and the physics seems sound. Yet when we point our telescopes at the sky, these predicted galaxies simply aren't there. The discrepancy was first noticed in the 1990s, when astronomers began conducting comprehensive surveys of our local galactic neighborhood. The Milky Way, according to simulations, should be surrounded by several hundred satellite galaxies of various sizes. Instead, we observe only about 50, and most of these are extremely faint and difficult to detect. The Andromeda Galaxy, our nearest large galactic neighbor, shows a similar deficit of satellite systems. Initially, astronomers assumed this was simply a matter of observational bias. Small galaxies are faint and difficult to detect, especially when they're overwhelmed by the light from their larger neighbors. Surely, the reasoning went, more sensitive telescopes and longer exposure times would reveal the missing galactic population. But as technology improved and surveys became more comprehensive, the missing galaxies remained stubbornly absent. The James Webb Space Telescope, with its unprecedented sensitivity to infrared light, was expected to finally reveal these elusive stellar systems. Its ability to peer through cosmic dust and detect the most distant galaxies in the universe seemed perfectly suited to solving the mystery of the missing galactic populations. Yet even JWST's remarkable observations have only deepened the puzzle, revealing a universe that contains fewer small galaxies than theoretical models predict, not more. To understand why this matters so profoundly, we must consider what galaxies represent in the cosmic hierarchy. They are not simply collections of stars scattered randomly through space, but complex, evolving systems that serve as the fundamental building blocks of cosmic structure. Galaxies are where most star formation occurs, where heavy elements are synthesized and distributed, and where the intricate dance between dark matter, normal matter, and energy plays out over billions of years. The formation of the first galaxies represents one of the most important transitions in cosmic history, the moment when the universe evolved from a relatively smooth and uniform state to the complex, structured cosmos we observe today. This transition, which occurred roughly 13 billion years ago when the universe was only a few 100 million years old, marked the end of the cosmic dark ages and the beginning of the epoch of reionization. During the dark ages, the universe was filled with neutral hydrogen gas that absorbed and scattered light, making the cosmos essentially opaque to electromagnetic radiation. The first stars and galaxies began to form within this cosmic fog, their ultraviolet light gradually ionizing the surrounding gas and clearing bubbles of transparency in the cosmic medium. These bubbles eventually merged, creating the transparent universe we observe today. Computer simulations suggest that this reionization process should have been driven primarily by countless small galaxies, each contributing a modest amount of ionizing radiation that collectively transformed the entire universe from opaque to transparent. If these small galaxies are missing, then our entire understanding of how the universe became transparent needs to be reconsidered. The mystery deepens when we examine the properties of the galaxies we can observe. The dwarf galaxies that do exist often show signs of having been dramatically affected by processes that stripped away much of their gas and halted their star formation. These galaxies appear to be the survivors of some cosmic catastrophe that eliminated their smaller cousins entirely. One leading theory suggests that the missing galaxies were destroyed by the very process of reionization they helped create. As the first stars and galaxies began pumping ultraviolet radiation into space, this energy heated the surrounding gas to temperatures exceeding 10,000 degrees. For the smallest dark matter halos, this heating may have been sufficient to prevent any further gas accretion, effectively starving potential galaxies before they could fully form. This process, known as reionization feedback, creates a natural cutoff in the galaxy formation process. Dark matter halos below a certain mass threshold simply cannot retain the gas necessary to continue forming stars. The galaxies that had already begun forming when reionization occurred might survive as small, gas-poor systems, while those that had not yet begun star formation would be permanently stunted. But this explanation, while elegant, raises new questions about the timing and efficiency of cosmic reionization. If small galaxies were responsible for reionizing the universe, how could the same process that they created have prevented their own formation? The answer may lie in the complex feedback mechanisms that govern star formation and galactic evolution. Supernovae, the explosive deaths of massive stars, inject enormous amounts of energy into their surrounding environments. In small galaxies with relatively shallow gravitational wells, these explosions can drive out significant amounts of gas, reducing the galaxy's ability to form new stars. Multiple supernovae occurring in rapid succession could potentially evacuate most of a small galaxy's gas reservoir, leaving behind a dark matter halo filled with old stars, but incapable of forming new ones. Recent observations with the Hubble Space Telescope have revealed that some of the faintest known galaxies contain surprisingly old stellar populations, suggesting that their star formation was indeed truncated early in cosmic history. These ancient stellar systems may be fossils from the epoch of reionization, preserving in their stellar populations evidence of the violent processes that shaped the early universe. The missing galaxy problem also connects to one of the most fundamental questions in cosmology: the nature of dark matter itself. The computer simulations that predict vast numbers of small galaxies are based on the assumption that dark matter consists of weakly interacting massive particles, or WIMPs, that cluster together under gravity but otherwise have minimal interactions with normal matter. However, alternative theories of dark matter could potentially explain the missing galactic populations. If dark matter particles can interact with each other through forces beyond gravity, these interactions might smooth out the smallest scale structure in the universe, preventing the formation of the low-mass dark matter halos that would host dwarf galaxies. Warm dark matter, consisting of particles that were relativistic during the early universe, naturally suppresses small-scale structure formation. Self-interacting dark matter, which experiences forces analogous to the electromagnetic interactions between normal particles, could also reduce the number of small dark matter halos. These alternative dark matter models might explain both the missing satellite problem in our local galactic neighborhood and the broader deficit of small galaxies throughout the universe. The implications of the missing galaxies extend far beyond academic curiosity about cosmic demographics. These absent stellar systems would have contributed significantly to the chemical evolution of the universe, synthesizing heavy elements in their stellar cores and distributing them through supernova explosions. Without these contributions, our models of cosmic chemical evolution may need fundamental revisions. The missing galaxies would also have affected the thermal history of the intergalactic medium, the diffuse gas that fills the space between galaxies. Their collective ultraviolet output would have influenced the temperature and ionization state of this cosmic web, potentially affecting the formation of larger galactic structures and the distribution of elements throughout space. Perhaps most importantly, the missing galaxies represent a critical test of our understanding of structure formation in the universe. The same physical processes that govern the formation of dwarf galaxies also influence the formation of larger structures, including galaxy clusters and the cosmic web itself. If we cannot accurately predict the abundance of small galaxies, how confident can we be in our models of cosmic evolution on larger scales? The search for the missing galaxies has led astronomers to push the boundaries of observational technology and survey techniques. Ultra-deep imaging surveys, capable of detecting galaxies millions of times fainter than can be seen with the naked eye, have revealed populations of extremely faint galaxies that were previously unknown. Some of these systems are so dim that they contain fewer stars than some globular clusters within our own galaxy. The discovery of ultra-faint dwarf galaxies has partially closed the gap between theory and observation, but significant discrepancies remain. Many of these newly discovered galaxies show clear signs of having lost most of their gas and suffered significant disruption from gravitational interactions with larger systems. They appear to be the remnants of once larger systems rather than representatives of a pristine population of primordial dwarf galaxies. Machine learning algorithms and artificial intelligence are now being employed to identify potential galaxy candidates in astronomical survey data, searching for subtle patterns and correlations that human astronomers might miss. These techniques have revealed previously overlooked populations of low surface brightness galaxies, stellar systems so diffuse that they were essentially invisible to traditional detection methods. The upcoming generation of extremely large telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, will provide unprecedented sensitivity for detecting and characterizing faint galactic systems. These instruments will be capable of obtaining detailed spectra of individual stars in nearby dwarf galaxies, revealing their ages, chemical compositions, and formation histories. Space-based surveys planned for the next decade will map billions of galaxies with exquisite precision, providing the statistical power necessary to test theoretical predictions about galactic populations. The European Space Agency's Euclid mission and NASA's Roman Space Telescope will survey vast areas of the sky, creating the most comprehensive census of cosmic structure ever undertaken. But even as observational capabilities continue to advance, the missing galaxy problem has evolved into something more sophisticated than a simple matter of detection limits. We now understand that galaxy formation is an incredibly complex process influenced by numerous physical mechanisms, from the properties of dark matter to the feedback effects of star formation and black hole accretion. The interplay between these various processes creates a rich tapestry of galactic evolution, where the same physical mechanisms that promote galaxy formation in some environments can suppress it in others. Understanding this complexity requires not just better observations, but also more sophisticated theoretical models that can capture the full range of physical processes operating in the early universe. Recent advances in computational cosmology have enabled simulations with unprecedented resolution and physical realism. These simulations can now follow the formation and evolution of individual galaxies, from the first collapse of dark matter halos through billions of years of cosmic evolution. They reveal a universe where galaxy formation is a delicate balance between competing processes, where small changes in initial conditions or physical parameters can dramatically affect the final galactic populations. One surprising result from these high-resolution simulations is that many of the predicted dwarf galaxies may have formed, but subsequently been destroyed through interactions with their larger neighbors. Tidal forces from massive galaxies can strip stars and gas from smaller systems, eventually disrupting them entirely. The stellar debris from these disrupted galaxies may still exist, distributed in faint stellar halos around larger systems, but the original galactic structures are gone forever. This process of galactic cannibalism helps explain why we observe fewer satellite galaxies than predicted. But it also suggests that the missing galaxies haven't truly vanished. They've simply been incorporated into larger systems. Astronomical archaeology, the study of stellar streams and substructure in galactic halos, is revealing the fossil remains of these ancient galactic interactions. The Gaia spacecraft, which has precisely measured the positions and motions of over 1 billion stars in our galaxy, has revealed numerous stellar streams and substructures that appear to be the remains of disrupted satellite galaxies. These discoveries suggest that the Milky Way has consumed numerous smaller systems throughout its history, gradually building up its stellar mass through a process of hierarchical merging. Similar evidence for disrupted satellites has been found around other nearby galaxies, suggesting that galactic cannibalism is a common process throughout the universe. The missing satellite problem may therefore be less about galaxies that never formed and more about galaxies that formed, but were subsequently destroyed through gravitational interactions. However, this explanation only accounts for some of the missing galactic population. Observations of galaxy clusters, which contain hundreds or thousands of individual galaxies, also show deficits relative to theoretical predictions. In these dense environments, tidal disruption alone cannot explain the missing galactic systems, suggesting that other physical processes must be at work. One possibility is that the formation of galaxies in dense environments is suppressed by environmental effects that don't operate in isolation. The hot, dense gas that fills galaxy clusters can strip away the gaseous reservoirs of smaller galaxies, preventing continued star formation and potentially halting their growth. This process, known as ram pressure stripping, is observed to affect galaxies in modern clusters, and may have been even more efficient in the past when clusters were denser and more active. The cosmic web itself, the largest-scale structure in the universe, may also play a role in regulating galaxy formation. Filaments of dark matter and gas that connect galaxy clusters create highways for matter flow throughout the universe. Small dark matter halos located along these filaments may experience different environmental conditions than isolated systems, potentially affecting their ability to form stars and evolve into visible galaxies. Advances in our understanding of black hole formation and evolution have also revealed new mechanisms that could affect early galaxy formation. Supermassive black holes, which are found at the centers of virtually all large galaxies, can produce enormous amounts of energy through accretion processes. This energy can heat and expel gas from their host galaxies, regulating star formation and potentially preventing the formation of new stellar systems. The discovery of supermassive black holes in some of the earliest galaxies observed by the James Webb Space Telescope suggests that these objects formed very early in cosmic history, potentially during the epoch when many of the missing galaxies should have been forming. The feedback effects from these early black holes could have contributed to suppressing galaxy formation on small scales. Recent theoretical work has also highlighted the importance of magnetic fields in regulating star formation and galactic evolution. Magnetic fields can provide additional pressure support against gravitational collapse, potentially affecting the efficiency of star formation in small dark matter halos. While magnetic fields are difficult to observe directly in distant galaxies, their effects on galactic dynamics and star formation may be significant. The role of cosmic rays, high-energy particles accelerated by supernova explosions and other energetic processes, is another area of active research. Cosmic rays can provide pressure support and heating in galactic gas, potentially affecting star formation rates and the retention of gas in small galactic systems. The cosmic ray pressure may be particularly important in dwarf galaxies, where other sources of pressure support are limited. As our understanding of galaxy formation has become more sophisticated, the missing galaxy problem has evolved from a simple question about galactic abundances to a complex investigation of the fundamental processes that govern cosmic structure formation. The answer likely involves multiple physical mechanisms operating across a range of scales, from the properties of dark matter particles to the feedback effects of star formation and black hole accretion. The missing galaxies also represent a profound reminder of the limits of our current understanding of the universe. Despite decades of advances in observational astronomy and theoretical modeling, we still cannot accurately predict one of the most basic properties of the cosmos: how many galaxies it contains. This humbling realization underscores the complexity of cosmic evolution and the challenges that remain in developing a complete theory of structure formation. The search for the missing galaxies has also revealed the remarkable diversity of galactic systems that do exist. Ultra-compact dwarfs, dark matter-dominated systems with extremely high mass-to-light ratios, galaxies with unusual stellar populations, and other exotic galactic varieties have been discovered through surveys designed to find the predicted missing populations. While these discoveries haven't solved the original problem, they have revealed that the universe contains a much richer variety of galactic systems than previously imagined. Future observations will likely continue to reveal new populations of faint galactic systems, gradually closing the gap between theoretical predictions and observational reality. However, it's also possible that the missing galaxy problem will ultimately require revisions to our fundamental understanding of dark matter, galaxy formation, or cosmic structure evolution. The story of the missing galaxies illustrates one of the most important aspects of scientific progress: the recognition that our models and theories, no matter how successful they may appear, are always subject to revision in the face of new observations. The universe has a remarkable capacity to surprise us, revealing phenomena and processes that challenge our assumptions and force us to develop more sophisticated theoretical frameworks. Dr. Sarah Chen, still working in her desert observatory as dawn approaches over the Atacama, represents the continuing human quest to understand our cosmic environment. The missing galaxies that puzzle her are not just abstract theoretical constructs, but fundamental building blocks of cosmic structure, whose absence challenges our most basic assumptions about how the universe works. As she prepares her latest analysis for publication, Dr. Chen realizes that the missing galaxies may ultimately teach us more about cosmic evolution than their presence would have. Their absence forces us to confront the complexity of galaxy formation, the limitations of our theoretical models, and the remarkable processes that have shaped the cosmic landscape over billions of years. The missing galaxies remind us that the universe is not a simple, predictable system that can be easily modeled with our current understanding of physics. Instead, it is a complex, evolving entity where multiple physical processes interact in ways that we are still struggling to comprehend. Each missing galaxy represents a puzzle piece in our understanding of cosmic evolution, and solving this mystery will likely require new insights into the fundamental nature of matter, energy, and structure formation in the universe. In the end, the story of the missing galaxies is still being written. Future observations, theoretical advances, and computational simulations will gradually reveal the fate of these absent stellar systems. Whether they were never formed, destroyed through cosmic violence, or hidden by observational limitations, their mystery continues to drive forward our understanding of how the universe evolved from a smooth, uniform state to the complex, structured cosmos we observe today. The missing galaxies serve as a reminder that even in an age of increasingly sophisticated astronomical instruments and theoretical models, the universe still holds profound mysteries that challenge our understanding and inspire continued exploration. They represent not just absent stellar systems, but gaps in our knowledge that point toward deeper truths about the nature of cosmic evolution and our place within the vast, ever-changing tapestry of space and time. As the sun rises over the Atacama Desert, casting long shadows across the ancient landscape, Dr. Chen closes her laptop and steps outside to watch the dawn. In the growing light, she contemplates the profound mystery she's dedicated her career to solving, knowing that the missing galaxies are out there somewhere in the cosmic darkness, waiting to reveal their secrets to a future generation of astronomers equipped with even more powerful tools and deeper theoretical understanding. The search continues, driven by the fundamental human desire to understand our cosmic origins and the processes that have shaped the universe we call home. The missing galaxies may be absent from our telescopes, but they remain present in our theories, our simulations, and our imagination, inspiring continued efforts to unravel one of the deepest mysteries in modern cosmology.